Today we're taking a look at section 6-5 on the central limit theorem, and we'll begin by looking at the theorem. The random variable x has a distribution that may or may not be normal with mean mu and standard deviation sigma. Simple random samples of all of the names n selected from the population. So those two are the given part of the theorem. Our conclusion. First, distribution of the sample means x bar. Let me get my pen working here so I can add in. Okay, distribution of the sample means x bar will, as the sample size increases, approach a normal distribution. The mean of the sample means is the population mean mu. So mu x bar is equal to mu. Number 3, the standard deviation of all sample means is sigma divided by the square root of n. Sigma sub x bar is equal to sigma over the square root of n. And this is called the standard error of mean. So a new term for us. Nice. Practical rules. If the original distribution is not normal, the sample must be of size n is greater than 30. If the original distribution is normal, the sample size may be n, so it could be smaller than 30. We now have two different z-score formulas that depend on the situation. We are working with an individual value from a normally distributed population. Z is equal to x minus mu divided by sigma. Okay, that's with an individual value, and that's what we're calling x. If we're working with a distribution of sample means, then what we have is x bar minus mu over sigma divided by the square root of n. Now that's a complex fraction, so just to show you where this came from, right, that actually this fraction means divided by, I'm going to put that at 1, divided by sigma over the square root of n. But we remember that fractions, when we divide, this is multiplying by the reciprocal. So if I put this in parentheses, you can see I get x bar minus mu times the square root of n over sigma. So that's where that comes from. And I find students do better if they use the formula rather than the one that the book has. So it's easier to enter on calculator for one thing. Okay, so let's talk about the differences between the two formulas. When do we use one? When do we use the other one? By looking at a couple of examples. And so we're starting with example 1. It's assumed that SAT scores are normally distributed with mean mu equal to 1518 and standard deviation sigma equal to 325. Okay, if one SAT score is randomly selected, find the probability that it is less than 1500. So in this case, it's one SAT score. Mean is 1518. Okay, so our 1500. And we want the probability it's less than 1500. That's our x. We need to change that x into a z. We know the mean is at 0. So z, and this is our old z-score formula, 1500 minus 1518 divided by 325. That's going to be negative 18 divided by 325. So negative 18 divided by 325. And I'm getting negative 0.055. So negative 0.06 would be my z-score. So I want to go to the negative table. 0.55 actually. Let's keep it as 0.55. No, we want a 6. Yeah, it only goes. The table only goes to the hundreds. Okay, so negative 0.06 So we're at the very bottom row. I want to go over to 06. It's 0.4761. So the probability x less than 1500 is, oops, I've got the 1 there, 0.4761. So that's the old type problem we've been doing. Now, let's do it with the 100 SAT scores. So part B, if 100 SAT scores are randomly selected, find the probability that they have a mean that is less than 1500. So notice the change here. We want the probability, the mean, not the individual value, but the mean is less than 1500. Well, we know that the mean of the sample means is the mean of the population, so we'll leave 1518 in the middle. This time we're working with x bar. Our picture looks kind of the same. The only difference is our z-score formula is going to be different. So we're going to have 1500 minus 1518 times the square root of 100 divided by 325. So that's going to be a 10 times a negative 18, which is negative 180 over 325. Negative 180 divided by 325 is negative 0.55. So there is quite a big difference in our two z-scores here. So let's look up negative 0.55. Okay, negative 0.55 is 0.2912. Okay, so we see there is a difference when we're working with the individual score and when we're working with the mean of a sample. All right, example 2. Membership in MESA requires an IQ score of 131.5. 9 candidates take IQ tests, and their summary results indicate that their mean IQ score is 133. Remember that IQ scores are normally distributed with a mean of 100 and standard deviation of 15. Part A. If one person is randomly selected from the general population, find the probability of getting someone with an IQ score of at least 133. So 100 is our mean. Well, and at least means greater than 133. So again, we're working with one individual. So 133 minus 100 divided by 15 equals 33 divided by 15. 2.20. Okay, so we look up 2.20 in our table. We get 0.9861. It's the area to the left of the z-score, so 1 minus that. So this is the probability x is greater than 133. So 1 minus 0.9861 is 0.0139. Okay, so that's the old way, working with an individual. Now we're going to work with a sample. This time we have a sample of size 9. If 9 people are randomly selected, find the probability that their mean IQ score is at least 133. Okay, so probability, I'm using actually greater than rather than greater than or equal to here. Okay, so our picture's again going to look pretty much the same. Okay, but the way we calculate C is what will change. We're going to do the 33 minus 100 times square root of 9 is our n over 15. So we have 33 times 3, which would be 99 over 15. And that's 6.60. There's a big difference between these two. Alright, so we go to the positive table to 6.60. If you look down at 3.50 and up, it's 0.9999. So our area here is 0.9999. So we need to take 1 minus 0.9999, which gives us 0.0001. So again, the probability changes by quite a bit.